Thank you. Our next speaker is Dmitry Bolotov.
Thank you very much for the opportunity to give a talk. And I don't. My talk will be not a long time. So my talk is titled "Foliation on closed three-dimensional Riemannian manifolds with a bounded modulus of mean curvature of leaves." Okay, now I want to maybe only represent my result, announce my result, and I think I will not do deep to details. Okay, thank you very much. Let us suppose that M be a close-oriented three-dimensional Riemannian manifold, and length F be transversally oriented smooth foliation of codimension 1. And we will assume that all objects will be smooth foliation and Riemannian manifold. Also, we suppose that all objects will be oriented. So let me recall my previous results. It is theorem 1. Let we fix it the constant V0, E0, and K0. And you see my, do you see my presentation? Yeah. Do you see my article? Excuse me. Okay. And let we have this constant, which is positive, and K0 is non-negative. And M be close-oriented three-dimensional Riemannian manifolds with the following properties. First, the sectional curvature is bounded above by the constant K0. And so we have injectivity radius of M is bounded from below. And this constant is a convexity radius of our manifold. And but it's important here that the injectivity radius is bounded from below. Okay. And let's H0 is one of follows constant. It depends on the K0. Okay, and X0 is a root of the equation here. Then a smooth transversally oriented foliation of codimension 1. The modulus of mean curvature of leaves, which is have such a property that a modulus of mean curvature is less of H0, should be taught. What is it taught? Taught is a foliation which for some metric, Riemannian metric on manifold, such that all leaves are minimal. All leaves are minimal. And it turns out, it's the taught foliation, there is an equivalent condition to foliation to be taught. This condition is the foliation doesn't contain generalized RIP component, so-called generalized RIP component. The RIP component, what is a RIP component? RIP component is a foliation of solid torus. It's a well-known part of foliation, but if foliation doesn't contain RIP components, but more the generalized RIP components, then such foliation is taught. That is, there is a Riemannian matrix such that all leaves are minimal. Minimal in the sense of mean curvature is identically zero. In this case, it was proved by Thurston and Eliasberg, but I think Gabai, that the number of cohomological classes that can be realized as Euler classes of tangent distribution to the tight foliation given on closed three-dimensional manifolds is finite. It means that only finite cohomological classes can be Euler classes of tangent distribution to the tight foliation. And give rise a very natural question. If we suppose that our foliation has a mean curvature of leaves bounded above by some constant, had we granted that the number of Euler classes, a number of homological classes can be realized as Euler classes tangent distribution to the foliation is finite. It turns out, and I now represent the following theorem. If we have positive constant V0, I0, K0, and H0, a fixed constant, such that first, the volume is bounded about by V0 section, but in previous theorem, we restrict the sectional curvature only from above. But now we module of sectional curvature of our manifolds is we are required to be bounded by the fixed constant. And injectivity radius also is bounded from below by the some constant. And in this situation, we also granted that the number of homological classes which are realized as Euler classes of distribution tangent to our foliation is infinite if we requires that the modulus of mean curvature is bounded from above by a fixed constant H0. So it is our result. Of course, such foliation with bounded mean curvature can be contain generalized RIP components, and it is actually a basic problem to how we can this fact is used in the proof. Let me don't want to explain the result. It is enough difficult, but let me explain you how we can due to torsion and to understand what is a Euler characteristic, how we can approach to the Euler characteristic of the distribution. Let us what we need to compute. Let us to understand what cohomological two-dimensional cohomological class what the how we can understand what cohomological what define what object are defined cohomological class. If we restrict the value this cohomological class on the basis of homological classes, then we actually almost have a full information of this cohomological class. And if we know these values, and therefore we can to understand how we can these values to these values to calculate. And it is enough, this person observes that this is enough geometric, it will be explained enough geometrically. Let me try to explain how we can this see. If we take the closed surface, but not necessarily connected, which relies basis class of homology, in two-dimensional homology, and embedded as an embedded surface in our three-dimensional manifold. And let us consider intersection of the foliation with our surface. We obtain, if we substitute our embedded, we can obtain so-called Morse foliation, which Morse singularities. From the condition of orientability of manifold and of our surface, we can to find a tangent to this induced foliation on surface, tangent vector field X. And we have singularities, standard singularities, which are saddles or centers. And if usual Euler characteristic can be calculated as sum of indices in these singularities. But in this case, we can to prescribe the sign to the singular point. If the tangent planes, if the normal to tangent distribution to foliation is coincide with the normal which determine the orientation of our surface is coincides, then these singular points have a sign plus if it is opposite orientation, this singular point is have a sign minus, and so Euler characteristic can be calculated as a sum of positive indices and minus sum of negative indices, where negative we calculate indices of such singular points which we have different direction of normals. Okay, yeah. I don't understand. So, and to calculate this Euler characteristic is the aim of this article, and it is enough difficult, but and exploit some geometrical properties of our foliation. For example, some properties of geometry which arise on RIP components. So thank you very much. Let me stop.
Thank you, Dmitry.